Hello there, Mr. Sutton here, bringing you the AB Calculus 5.5 classwork solutions on RAM Part 2. For this problem, we want to figure out if approximating this integral with LRAM is going to give us an over or underestimate. So to figure this out, we need to figure out if this is an increasing or decreasing function on the interval from 3 to 8. To do that, we take the first derivative. That'll be 3x squared, or actually negative 3x squared, plus 6x. And then let's find some critical values to see if any of them fall on this interval. Take a negative 3x out of there. We've got x minus 2 inside, and we can set all of that equal to 0. That gives us the critical values of 0 and 2, neither of which falls on the interval from 3 to 8. So whatever result we get when we do sign analysis from something from 3 to 8, it's going to be for that whole interval. So let's just randomly test a number between 3 and 8 in our first derivative. If I test the number 4, I'm going to get a negative times a positive, which is negative. That means that this is a decreasing function, so therefore LRAM is going to over-approximate. On this problem, we want to know if RRAM is going to under or overestimate this integral right here. So to figure that out, we need to figure out if this is an increasing or decreasing function. I'm going to rewrite this function as f of x equals 4 plus x squared quantity raised to the negative 1. And now I'm going to go ahead and take the derivative to see if I can figure out whether this is increasing or decreasing between 2 and 5. So using my power rule, this is going to be negative all of this to the negative 2 times the tail of 2x. So now I'm going to set this equal to 0 and see what critical values I can find. And I'm just going to write this as negative 2x over this stuff squared. So in terms of critical values, we can definitely zero out this fraction by plugging 0 in for x. So we've got a critical value at 0. And down here, there's really nothing we can do to zero out the denominator, so we don't have to worry about this thing being undefined anywhere. So 0 is the only critical value. That does not fall between 2 and 5. Therefore, whatever I test between 2 and 5 is going to speak for the whole interval. Let's go ahead and try 3. If I plug 3 into this first derivative, that's going to be a negative over a positive, which is negative. Since I have RRAM on a decreasing function here, RRAM is going to underestimate a decreasing function. So that's our answer. RRAM is under. For this problem, we're trying to figure out if LRAM will under or overestimate this integral. So to do that, let's figure out if this is an increasing or decreasing function in the integrand. Taking the derivative of 2e to the x to the minus 1, we've got 2e to the x minus 1 as the derivative. It's just 2 times e to the something, and we have a tail of an invisible 1 there. So let's set this equal to 0 and see what we can find. There is no way to zero out an exponential function, so there's actually no critical values here, which means that whatever we test really anywhere is going to speak for all the possible x values in terms of increasing or decreasing. So let's go ahead and I'm just going to plug in 0. That's a pretty easy number. If I plug 0 in here, this has to come out positive. E to the whatever always comes out positive as long as there's no negative out in front. Since that's greater than 0 and we have LRAM on what is shown to be an increasing function here, LRAM is going to underestimate on an increasing function. For this problem, we're being asked to express this integral as a Riemann sum. So the general setup for that, we're going to have the limit as n approaches infinity of the summation from 1 to n of f of x sub I times delta x. So all this stuff, we got to turn this into this, which means we have to figure out how to express all of this in terms of n. N is the magic letter here because that's what's changing. All right, so let's start with this delta x. Delta x is just going to be the distance between the limits of integration divided by the number of subintervals, which is n in this case. So that's going to be, in general, b minus a over n, so it's going to be 0 minus negative 2 over n, or 2 over n. Next, to figure out this f of x to the I, we're basically going to have something plus 3 squared. We just have to figure out what the something is. The something is going to be the starting value plus I times delta x. So that's going to be, in this case, negative 2. That's the very first x value, negative 2, the lower limit of integration, plus I times this 2 over n that we just found. All right, we actually are ready to put it all together. So we're going to have limit as n approaches infinity of the summation of, now we're going to have, we're going to apply the function here to this input. So we're going to have negative 2 plus 2i over n plus 3, all of that squared, and then instead of dx, I'm going to have delta x, so 2 over n. So all this stuff in here, except for the 2n out there, all the stuff in here, that was the f of x sub I, and then this 2 over n, that is your delta x. On this problem, we need to express integral from 0 to pi sine of x dx as a Riemann sum. So we want the general form, limit as n approaches infinity of summation from 1 to n of f of x delta x. So to get this, let's start by finding delta x. That's going to be basically the interval length divided by the number of subintervals, which in this case is n. So this is going to be, in general, b minus a over n, so pi over n. And then we're going to use this to figure out this f of x sub I. X sub I is basically just the first term, or the first x value, plus I times delta x. So in this case, x sub I is going to be 0 plus I times pi over n, so pi I over n. And then we're going to plug all that into the actual function. So instead of writing f of this stuff, I'm going to write sine of all this stuff. And then we'll also have a times pi over n for that delta x there. For this problem, we need to express the Riemann sum here as a definite integral. So we're trying to go from this format to this format here. So let me first figure out what the general function in here is. To do this, I'm looking to see an expression that has like a constant plus something I over n. This 4 plus 2i over n looks pretty convenient. So we're going to think of this stuff in here as just being x when I go ahead and write my integrand. So I've essentially got the integral from something to something of 2x squared. Now I just have to find what my limits of integration are going to be. So the lower limit is going to be the number that's being added inside here. So we're going to have a value of 4. The b value is going to be this a value of 4 plus, well, whatever number's on top of the n over here, because this is always going to be your interval length, because normally this is delta x, so this is your interval length divided by the number of intervals. That tells you how much your delta x has to be. So we end up with then 4 plus 2, because of this 2, so that gives us a b value of 6. So then we've got the integral from 4 to 6 of 2x squared dx. On this problem, I need to express this craziness in definite integral form. To do that, well, let me just look at my general format. I need integral from a to b of some function, dx. I'm going to start by figuring out what the function's going to look like. So in general, I'm looking for some expression that has a constant plus something with an I over n. This negative 3 plus 3i over n looks like it'll do. So I'm going to think of this chunk of stuff as an x. So then my function is going to be 4x squared minus 5x and then minus 1. Now I just need to find my limits of integration. First limit is going to be whatever number is being added to the something I over n in that x value there. So that's going to be negative 3 for the a value. And to get the b value, I just have to add whatever this interval length is up here. This is normally delta x, so it's interval length over number of subintervals. So we're essentially doing, to get b, we're doing negative 3 plus 3, which is going to come out to 0. So now I've got the integral from negative 3 to 0 of 4x squared minus 5x minus 1 dx. On this free response problem, we've got a table of information about the derivative of the radius of some balloon that's being expanded. problem C here, part C, they want us to use a right Riemann sum with 5 subintervals, indicated by the data in the table, to approximate integral from 0 to 12 of r prime. And then, using correct units, explain what all that means in terms of the radius of a balloon. All right, so let's find our integral first. Since we're doing RRAM, that means when we look at our table, we're going to take the right endpoint of each of these rectangles. So we can say integral from 0 to 12 of r prime t dt is approximately equal to, and now we do our rectangles. We have a base of 2 times a height of 4, because this is RRAM. We're picking 4.0 instead of 5.7. Note the approximately equals here. On a free response, you will lose points if you write equals, because this is supposed to be just an approximation. All right, so next we have plus the base of 3 times a height of 2, plus base of 2 times height of 1.2, plus 4 times 0.6, plus 1 times 0.5. Now, this was a no calculator question, so you did actually, if you wanted to get a single number of this, you needed to do it by hand. So we've got 8 plus 6, that's 14, plus 2.4, that's going to be 16.4, plus another 2.4, that's going to be 18.8, plus 0.5 is going to be 19.3. And that's going to be in feet, because we're basically finding the area under the curve, which is feet per minute. So if you're doing that, if you're essentially multiplying all these bases times heights, the bases units are going to be time, and the height units are in feet per minute. So feet per minute times minutes cancels out minutes and leaves us with feet. That's the short explanation for what's going on there, without knowing some more heavy-duty theory here. So now let's explain what all this means in terms of the radius of the balloon. This means that the radius of the balloon increases by 19.3 feet over the interval from 0 to 12. So a few things that are important here. You got to have the feet. You also have to mention this time period of 0 to 12 minutes. If you don't mention 0 to 12, you're not being specific enough. For part D, they want to know if our approximation in part C is greater than or less than the true value of the integral from 0 to 12 of r prime of t dt, and then give a reason. So here's where we're really happy that we wrote approximately equals in part C instead of equals, because if we wrote equals, then this would kind of be a moot point, because then what we said in part C would be exactly the value of this integral, but it's not. So is our part C estimation greater than or less than? So part C estimation was a right Riemann sum. So the question here is the thing that we're trying to find the area under, is that increasing or decreasing? Is r prime increasing or decreasing? And that'll tell us everything we need to know, combined with what kind of RAM we were using. So looking at the problem here, the key passage, part of the passage, is for 0 less than t less than 12, the graph of r is concave down. Well, if the graph of r is concave down, that means that r prime must be decreasing on the interval from 0 to 12. And if r prime is decreasing, then r ram is going to under-approximate the true value of the integral.